Alright, dear children of class 12 science, we do one important topic related to this diffraction due to single slit, the problem for diffraction due to single slit. And this is actually a topic from where we do numericals also. It is angular width of central maximum. You know, the center part of the diffraction pattern is always a bright fringes. That's why that band is called central bright band, also called principal maximum. But that principal maximum central bright band has an angular width. What width? Angular width. So what is angular width of central maximum? It is the angular position between the first secondary minima on the two sides of central maximum. The angular position between first secondary minima on two sides of central maximum is actually measured as angular width of central maximum. So in order to measure this angular width of central maximum, so I start with the condition of first secondary minimum. And you know, for first secondary minimum, children, you have learned this part in the last YouTube video. The first secondary minimum, in the first secondary minimum, the condition of first secondary minimum is what? E sine theta 1 equals to lambda. Yes, you have learned it already. In case of condition for secondary minima, the first condition, secondary minimum is given by E sine theta 1 equals to lambda. Means this is the path difference. So this path difference E sine theta 1 equals to the wavelength of light, which is equals to lambda. So if E sine theta 1 equals to lambda, then I can write down sine theta 1 equals to lambda by E. So this E I'll take in the denominator. And children, you know what is E? E is the width of the slit. E is the what? Width. W-I-T-H, width of the slit. Okay. So if theta 1, sine theta 1 equals to lambda by E, then I write this way also. Theta 1. So if I write theta 1, then sine, if I remove from left hand side, on the right hand side, it will be sine inverse. It will be sine inverse lambda by what? E. So this angle, theta 1, which is the angle of diffraction made by the first secondary minimum, is also measured as the half angular width. This is the half angular width of what maximum? Central maximum. And children, for this measurement of half angular width and even the measurement of angular width of central maximum, that you learn in the next YouTube video, okay, basically with the graph, okay, and that from that graph you understand better also. But the expression of half angular maximum means theta 1 equals to sine inverse lambda by E. And when you measure this angle, we measure this angle in degree. We measure this angle in what? Degree. Okay. So half angular width, also called semi-angular width, is given by theta 1 equals to sine inverse lambda by E. Okay. But actually we have to find angular width of central maximum. So what I do, I write down this way, since secondary minimum, first secondary minimum. Okay, first secondary what? Minimum is formed on both sides of what maximum? Central maximum. Both sides of what maximum? Central maximum. So with the central maximum, first secondary minimum angle made by the first secondary minimum is theta 1. With the central maximum, the another secondary minimum, first secondary minimum also makes same angle. So to measure the angular width of central maximum means it will be like this. So let me just show you this way. If this is the central width, if this is the central maximum, suppose if this is the central maximum, then this is the first minimum. This is also the first secondary minimum. So with respect to this central position of the central maximum, so I can draw a line and see an angle. That is the angle made by the angular separation between the first two secondary minimum on either side of central maximum. And this angle is actually measured as angular width of central maximum. With the what maximum? Central maximum. So I'm telling you children, so with the graphical method, I'll show you this and measure this angular width of central maximum also. But as for the calculation we are doing, okay, this angle, just let me tell you this way. Suppose this is the line which I'm drawing. This angle is theta 1. This is the angle made by the first secondary minimum with the central maximum. So on the right hand side. So on the left hand side also, this is the first secondary minimum. This secondary minimum also makes same angle, theta 1. So if I double this theta 1, that give you the angular width of central maximum. Because this is half angular width, double of this half angular width of central maximum. That's why angular width of what? Central maximum is actually measured by 2 theta 1. Double the half angular width, that is the angular width of central maximum. Okay, now it will be 2 theta 1 is how much? Sine inverse lambda, this is lambda by E. So 2 theta 1, so if you look at this expression, 2 theta 1 is this much. So 2 theta 1 is the angular width of central maximum, which equals to 2 sine inverse lambda by E. But when you measure this angular width, again I repeat, this angular width we measure in degree. But children, when we see this diffraction pattern experimentally, this angle which is formed by the minimum are very small angle, and this angle can be measured in radian also. We measure in what? Radian, which means if theta 1 is very small, then that angle we measure in radian, then what we can do, we can write this way also, sine theta 1 equals to theta 1. You know there is a condition, when theta is very small, sine of theta is theta. In a similar manner, theta 1 is very small, which are very small angle which is formed, so that's why sine of theta 1 equals to theta 1. So with this also we measure the angular width of central maximum. So look at it, if I take sine theta 1 is theta 1 and we measure this angle in radian, then this relation again can be written as sine theta 1 equals to lambda by E. But sine theta 1 I write down as what? Theta 1. So theta 1 equals to lambda by E. So theta 1, which is lambda by E, is the half angular width when we measure this theta 1 in radian. Okay, but angular width means 2 theta 1, and just double this, it will be 2 lambda by E. So children, look at the expression. So angular width of central maximum is also measured in terms of radian when theta 1 is very small and is given by 2 lambda by E. So this is also the expression, we measure the angular width of central maximum. But children, this angular width which we measure is basically in radian. Now from here I can make a conclusion. Angular width of central maximum increases when the wavelength of light increases. Means angular width and wavelength are directly proportional to each other. Similarly, angular width of central maximum is inversely proportional to E, the width of the slit. If you take the width of the slit smaller, more the angular width. More the angular width means your central maximum become broader. This central maximum become broader when angular width become more. But this angular width can be increases even by decreasing the width of the slit. That's why angular width of central maximum depends upon the wavelength of light, incident light, and even the width of the slit. Now the next thing that we do measure out here is the condition for secondary maxima. See, we discuss condition for secondary minima. Then after, from there we measure this angular width of central maximum. Now we do condition for secondary maxima. Now to make the expression for condition for secondary maxima, maxima means bright fringes. Okay, it is always observed in the diffraction pattern is that between two consecutive minima there are the central there is a secondary maxima. So for that, let me show with a diagram. So if you refer this diagram, this is the diffraction pattern observed by the Fraunhofer due to single slit. This is central maximum. Secondary minima, first secondary minima, second secondary minima. But between two secondary minima, what is there? Secondary maxima. Again, between two secondary minima, what is there? Secondary maxima. So that means between every two secondary minima, there is a secondary maxima. So if you know the condition for secondary minima, we can even write the condition for secondary maxima. Now for this, let me just take for first secondary minima. Just let me write down. This is for first secondary minima. You know, for first secondary minimum. Let me write down minimum. You know what is the condition you learn? E sine theta 1 equals to what? Lambda. For secondary minimum condition, E sine theta 1 is lambda. Second secondary minimum condition. Second secondary minimum. For second secondary minimum, your path difference E sin theta 1, theta 2, actually this is theta 2, is 2 lambda. So it will be the multiple of lambda and on. That means lambda, 2 lambda, 3 lambda, it will go on. But as I said, between first secondary minima and second secondary minima, what is present? First secondary maxima. What will lie? First secondary what? Maxima or maximum. Let me use the word maximum. So from here we can measure the path difference of first secondary maximum. And the path difference of first secondary maximum is the mean path difference of these two minimum. So mean path difference means lambda plus 2 lambda by 2. Just add these two path difference, divide by 2, which means 3 lambda by 2. So see, to get first secondary maxima, the path difference must be 3 lambda by 2. So for first secondary maxima, the path difference, so I write E sin theta 1, it must be 3 lambda by 2. Means the odd multiple of lambda by 2. Similarly, if I do for secondary maximum, the path difference E sin, okay, let me write theta 2 will be 5 lambda by 2. So we just follow the sequence. What? Odd multiple of lambda by 2. 3 lambda by 2, 5 lambda by 2, then 7 lambda by 2, it will go on and on. So in this way, if I write down the condition for mth secondary maxima, this is for mth secondary what? Maximum. A path difference E sin theta m, I write down this way only, will be 2m plus 1 lambda by 2. So I am writing general E sin theta m is equals to 2m plus 1 lambda by 2, where in the expression of this path difference m actually starting from 1, 2, 3 dot like that. But student, what I do, I put what sign? Plus minus sign. You know why? Because your secondary maxima is formed on both sides of central maximum. Now this is a general condition for the formation of secondary maxima. So if I put m equals to 1 in the expression, I get exactly this one, E sin theta 1 equals 3 lambda by 2. If I put m equals to 2, that is for second secondary maxima, I'll get E sin theta 2 equals to 5 lambda by 2. Which means in general, what is the condition for secondary maxima? Is nothing but path difference E sin theta m must be equals to plus minus 2m plus 1 lambda by 2. But this plus minus sign, as I said, indicates that the secondary maxima is formed on both sides of central maximum. That's why it can be on positive side, it can be on negative side. That's why this plus minus sign has been used. So children, I have explained in details about the condition for secondary maxima, and even we measure the angular width of central maximum. So we do this much today, and we do continue with the other topic from this chapter. Thank you so much.